Okay, in this lesson, we're going to continue looking at forces a little bit longer because there's a couple more things I wanted to point out. And this time, I'm going to look at the Mks system of units. And so when we're working with this international system of units, or, Système International is how you'll see it sometimes, SI, it's the standard of measurements that they use are the meter and the kilogram and the second. Okay? So in imperial measurements for the US, generally we use different measurements, pounds, feet, things like that. But what we're going to be working with is kilograms, meters, and seconds. All right, so meters, kilograms, and seconds. And so let's go take a look back at this object here. In fact, we're going to do a couple things. One, right back over in here, under here with the physics. For each one of these, notice how I was saying they indicate a mass of 1, and I just left it there. Well, that really means 1 kilogram, all right, because that's the standard unit within this system, is 1 kilogram. And that's because if you take a look at, let me get my cursor up here again, my tool. So if you take a look at this, a newton, 1 newton, is equal to 1 kilogram. So that's a kg. So I'll put a little g like this because it's not a capital. 1 kilogram times meters per second squared. Here's my meters per second squared. Right? So from the previous lesson, we'd calculated each one of these to have a force of 9.8 newtons. Right? So if I was to multiply this times 9.8 on this side, then I'd have to multiply this times 9.8 on this side to balance out the equation. And that's where my 9.8 meters per second squared would come in. So 9.8 newtons would be 1 kilogram times 9.8 meters per second squared, because I'm leaving the 1 kilogram mass in place. So this represents a mass of 1 kilogram. All right, so that's really the point I wanted to make about that when working with these. So these are just fundamental units: meters, kilograms, and seconds. And then the other thing I wanted to point out in here was this in here. So I did go verify that it wasn't so exactly precise, it was still moving it. So what I'm going to do is I'm just going to take this cube out of the equation here, and this ended up, this length, this joint that we have in here, is what was affecting it. So here's my rigid body joint for this. I'm just going to take it out of there so it's not connected. I'm just going to move this cube out of the way. Now my force I was applying still to this cube, as you can see in the game logic here. That's where I had the keyboard set up, and there's my force of 19.7. I had tried that time. Let's do 19.6, where we know that should balance out the force exactly. Or no, not in this case. We only have 1 cube, so 9.8 newtons is going to be our force upward. Right, so this is really common. You're going to see a lot of this. You're going to see forces projected upward and downward, and that's where back in these vectors really becomes a big deal, where we're talking about the direction for I, j, and k, and negative I, negative j, negative k. Right, so forces upward are going to be, with with k, and downward negative k. So it's really, if it's just going up and down, that depends on negative or positive. Positive or negative is how you would express it, right? And that's why this has a positive force upward of 9.8 newtons, like this. So now when I run it, it's going to fall to the ground. Now I'm going to use the M key. Now, all right, I'm pressing the up arrow key, and it's just not moving at all. It's just solid as a rock on the ground. So it must have been the connection between using these rigid body joints that messed up that calculation by that very small amount. But those are just things to look for. I said let's make this 9.85, just a little bit extra force in here. Let's run it and see what happens. It should just slowly move it upward. And it is. You can just barely see it, right? Like that. In fact, let's see if we can figure out what force they're using. I'm thinking they use 9.81 for the acceleration of gravity, 9.81 meters per second squared downward. So now this should bounce it off. This for me, this should stay solid on the ground too. And well, now we can see it's just barely moving. Let me zoom in. Let's see if it actually lifts it up. Yeah, it does lift it up. So I guess they are using 9.8. It's hard to say. But so Oh, well, wait a second. Nope. In this case, let me change one other thing because I didn't. In this case, I don't think I have my precision set back in here. Well, my unit. Oh no, there's my substeps. So now they say gravity is 9.8, and I have my force at 9.81. Let's just see if it's actually true. Let's see if it lifts it up. Yeah, it is at 9.81. When I have my force at 9.81 newtons, it is lifting it up. So, well, let's verify that. Let's change the gravity. We can change gravity, right? So I'll put it at 9.81. Let's see if that exactly balances out the 9.81 newtons that I have in there. And sure enough, I'm holding down the up arrow key, and it's not moving at all. All right, so these are really important concepts to be aware of, because later on, not so much in this tutorial, but for the next tutorial series or a couple other tutorial series that I'm doing, we're going to be dealing with forces in these directions, you know, besides just perpendicular directions, up, down, east, west, left, right, all that kind of stuff. And then that's where those unit vectors are going to come into play that we calculated a couple of units back, because without that knowledge of those unit vectors, then we won't be able to figure out what the forces are, the component forces in X, Y, and Z, if a force is, say, moving along this direction like this. Now for now, and for probably the next couple tutorials, we'll primarily work in Cartesian coordinates. Notice when I was specifying the point for this vector, I was doing it by, this was, what would I say, it was a 2.828, you know, over in X, 2.828 in Y, and in one of the earlier tutorials when I was moving the one on the plane like that. So I was specifying it in Cartesian coordinates, but in other lessons we'll work in cylindrical coordinates, which is basically specifying it around the shape of a cylinder, and in spherical coordinates, specifying it in using basically the shape of a sphere. So they all matter depending upon the type of problem you're working on. Okay, well that's it for now, and I'll see you in the next lesson.